cold fusion could save the world. Unfortunately, it's got somewhat of a flaky reputation. But today I have some quite remarkable news. A group of physicists say they know how cold fusion works theoretically. Someone just needs to do it. And that's a welcome change from people with devices that don't work even theoretically. So let's have a look. When two small atomic nuclei join to form a larger one, enormous amounts of energy can be released. The problem with this nuclear fusion is that atomic nuclei are all positively charged. For them to fuse, one has to overcome the electric repulsion between the nuclei until the strong nuclear force takes over. Crossing this so-called Coulomb barrier requires a lot of energy at first, but the fusion itself frees more energy than it requires. Usually one tries to cross the Coulomb barrier like the sun does, with enormous heat and pressure. Cold fusion, in contrast, is the idea that one doesn't need this, that instead one can deposit the nuclei into some solid-state material, and that this will lower the electrostatic repulsion between them. Usually one uses deuterium, that's an isotope of hydrogen, as the nuclei to fuse, and puts it in a metal like palladium for the solid-state object. Cold fusion has an unfortunate history of fraud, hype, and just bad science, which we talked about in an earlier episode, but it's not all bad science. There's reliable evidence that some solid-state materials actually do enhance nuclear fusion rates. Sandia Lab, for example, builds a device called the Nutristor that sends a low-energy beam of deuterium into a titanium plate. The deuterium accumulates in the plate until it starts to fuse. This emits neutrons, so they use it as a neutron generator. However, it's an example of cold fusion, just that the beam takes more energy to create than one gets out from the fusion. There's also been tentative evidence that aiming a pulsed laser at the palladium with deuterium will stimulate fusion for specific pulse frequencies. This suggests that phonon excitations have something to do with it, though this finding hasn't been replicated consistently. The authors of the new paper now say there are 3 separate mechanisms for cold fusion. Each on its own is too small an effect, but all 3 together could just make it work. The first mechanism is in the atomic range. Remember that the problem with nuclear fusion is the electric repulsion between the nuclei. Now imagine you could put a thin slice of negative electric charge between them. Then the nuclei wouldn't notice each other as they get closer. Something similar could happen in solid-state lattices near defects where the electron wave function becomes focused and forms a sort of shield between the deuterium nuclei. In the paper they write that this can enhance the fusion rate by a whopping 25 orders of magnitude. The second mechanism they discuss is nuclear resonance between several of the nuclei that you want to fuse. This can be triggered, for example, with the pulsed lasers that I mentioned earlier. They say that the reason this works is that it causes a deformation of the nuclei that effectively lowers the energy you need to make them approach. Unfortunately, creating this resonance eats up energy similar to what would be released during the fusion. They conjecture, however, that similar resonances could exist at lower energy and estimate that this could lead to an enhancement of 7 orders of magnitude of fusion probability. The third mechanism they discuss in the paper is that the presence of the larger nuclei in the material facilitates the fusion of the smaller nuclei by aiding a quantum tunneling process. This superficially makes sense because we know that nuclei can aid quantum processes that are otherwise impossible. For example, an electron can normally not just emit a photon. However, put the electron in the vicinity of an atomic nucleus, and that process can happen thanks to momentum exchange with the nucleus. For cold fusion, they say something similar takes place. The small nuclei that you want to fuse can temporarily borrow energy from the surrounding nuclei, fuse, and then give that energy back. They estimate that this could lead to an increase of fusion rates upwards of 30 orders of magnitude. Take it all together, they say, and these effects can enhance the fusion rate in materials enough for it to produce net energy. They also outline ways to test these individual mechanisms to learn more about them, most importantly by using specific materials that have controlled amounts of traces of other elements in them. If you've already forgotten half of what I said, I made a quiz that lets you check how much you remember. What are we to make of this? I suspect that the first effect, the atomic one, exists but happens too rarely. The second one exists but eats up too much energy. And the third one I'm not sure exists, which in other contexts is called the Holy Trinity. That said, I strongly support further studies on cold fusion, because these are low-cost, small lab experiments with a potentially huge payoff. And if it works out, not only would we have basically unlimited clean energy, we'd also have amazing material for a blockbuster movie. It could be called Honey, I Shrunk the Coulomb Barrier, or The Man Who Knew Too Much About Palladium. No, I know. Fusion, actually. I expect royalties. Scientific progress is difficult to predict, but human behavior isn't. And so today I'm going to make a big and bold prediction. Geoengineering is coming. We're going to meddle with the climate. But not in the way you've been told. Climate engineering, sometimes called geoengineering, is the deliberate tampering with Earth's climate in the hope of improving human well-being. The most discussed option is stratospheric aerosol injections. That's the idea of spraying tiny particles, that's the aerosols, into a layer of the upper atmosphere, that's the stratosphere, to reflect sunlight and cool Earth. Another idea for climate engineering is marine cloud brightening. This works by spraying sea salt into existing clouds over the oceans to make them whiter, so that they reflect more sunlight. One can also dump iron into the ocean so that algae take up more carbon dioxide, or pour silica microbeads into the Arctic Ocean to make ice temporarily more reflective, or to pump around water in the Arctic to thicken ice layers. What these methods have in common is that they're inexpensive and don't require many actors. The costs to stop further warming with stratospheric aerosol injections, for example, has been estimated to be just about $30 billion per year. That's maybe not your idea of cheap, but it's basically nothing compared to tens of trillions that the energy transition will take up. These measures have been hugely controversial, primarily because they do nothing about the root problem, which is the increase of atmospheric carbon dioxide. Their attempts to remedy the worst consequence, temperature increase, but wouldn't do anything about other problems such as ocean acidification caused by the carbon dioxide, and they're likely to change global rainfall patterns. Probably because really we don't know. Attempts to scientifically study the consequences have been shut down by environmental activists repeatedly. In March last year, Harvard University was forced to discontinue an experiment to test stratospheric aerosol injections. In May, Washington University had to put a marine cloud brightening project on an indefinite pause, allegedly due to health and environmental concerns. And the startup Make Sunsets, which did some tiny, unauthorized stratospheric experiments launched from Mexico, triggered the Mexican government to ban all geoengineering. Most countries, however, have no laws on geoengineering, and at a meeting last year, the UN didn't come to any resolution on what to do about it. The UK government recently put money into further studies. Most of the attention has gone to stratospheric aerosol injections because that'd be a global solution. But I think this isn't how things will go. First of all, I don't know about you, but personally I think $30 billion a year is still a lot of money. Also, normal airplanes don't fly in the stratosphere, and it's probably not the best time to ask Elon Musk. Last time I looked, he was busy insulting the British Prime Minister. Instead, what we'll likely see is an increasing amount of local weather modification programs that take the edge off heat waves, droughts, wildfires, and maybe at some point even hurricanes. And if you change a lot of weather, you change a little of the climate. Marine cloud brightening is an example of this. Then there is cloud seeding, a method to make clouds rain off when and where you want. China has a cloud seeding program that employs more than 30,000 people. That's a lot of people telling clouds what to do. India has used it to try and clean the polluted air over megacities, and the governments of Indonesia and the Philippines took to cloud seeding to combat wildfires. Basically, what we're going to see is a global game of weather modification with consequences that'll usually be downwinds, and that's normally in the east. For example, researchers from UCSD used climate models to study the impacts of marine cloud brightening off the US west coast. They found it could indeed reduce the risk of high temperatures in the US. However, it also decreased rainfall in that area and caused more frequent heat waves in Europe. And someone might want to look into what cloud seeding over China does to rainfall in California. I don't advocate geoengineering as a good solution. It isn't. But I think we'll do it anyway, and not just because it's inexpensive. If you reduce carbon dioxide emissions in your own country or even as a person, the benefits will be distributed over the entire planet. Especially if you're a small country, you won't see much benefit from your own actions. It's a classical example of a collective action problem, and we've spectacularly failed at solving it. But geoengineering will benefit the people in your country. It'll prevent deaths during heat waves. It'll increase crop yields. It'll get politicians elected. It will happen. And that's why it's a bad idea to protest research on it. The more we know about the consequences, the better we'll be prepared. And it's about time we prepare, because maybe soon the weatherman will say, "Today's weather is brought to you by ExxonMobil, sunny with a chance of corporate intervention." Particle physicists are spinning a new story. It's that measuring something about neutrinos will tell us why we exist, why we're here at all, why the universe contains something rather than nothing, or why the universe didn't disappear. This supposedly justifies the approximately $2 billion that went into Fermilab's Dune experiment. Fermilab is the premier particle physics labs in the United States near Chicago. It was host to the Tevatron, the world's largest particle collider, until the Large Hadron Collider went online. Its experimental collaborations discover the top quark, that's the heaviest of the quarks, in 1995. Fermilab's new flagship project is Dune, the deep underground neutrino experiment. Its task is to shoot a beam of neutrinos through the Earth's crust from Fermilab to Sanford Lab in South Dakota, about 1,300 kilometers away. Last year in the summer, they observed the first neutrinos with a prototype detector. Neutrinos are often called ghost particles because they mostly go through matter undisturbed. The idea that Dune will unravel the mystery of our existence comes from it measuring CP violation among neutrinos. It's this CP violation that particle physicists claim is related to our existence because, they say, it's necessary to explain why there is more matter than antimatter in the universe. Particle physicists think matter and antimatter should have been created in the same amounts in the early universe. But if that would have been the case, then matter and antimatter would all have annihilated, and the universe would now be filled only by radiation. We know that CP symmetry is violated among other particles, but that isn't enough to explain why we're here, they say. There is some tentative evidence that CP symmetry is indeed violated for neutrinos from earlier experiments at 2 to 3 sigma. The task of Dune is supposed to settle the case. The story that this tells something about our existence does not come from ill-informed science writers. It comes from scientists themselves. In a recent press release, for example, Alexandra Sousa from the University of Cincinnati said the purpose of the experiment is that we're trying to understand why we're here. The website of the experiment too claims that this research may give us the key to understanding why we're here at all. Spoiler alert, it won't do any such thing. First, Even if we knew why there was more matter than antimatter and it did not all annihilate to radiation, this would not, as Quantum Magazine put it, explain why the universe contains something rather than nothing, because radiation is still something. Second, that matter exists is not sufficient to explain why we exist. Leaving aside that I believe there's a difference between a person and an electron, even if you explained why more matter was created than antimatter, it'd just move the question to why the thing existed that they were both created from. The third problem is that estimates say that even if we observed CP violation in the neutrino sector, it wouldn't be large enough to explain the observed matter dominance, at least not according to the simplest theory. This brings me to the fourth and biggest problem, which is that really we don't know how either matter or antimatter was created, so there isn't any problem to solve. We don't know now, and we won't know once we have the results from the experiment. The currently most popular theory for matter and antimatter creation goes like this. Brace yourself. The universe was created from a quantum fluctuation of a field called the inflaton. There's no evidence for such a quantum fluctuation or such a field. This inflaton field then decays into a lot of other particles, including right-handed neutrinos. There's zero evidence that these right-handed neutrinos ever existed. And those right-handed neutrinos then further decay into matter and antimatter, which then needs the CP violation. That's a lot to swallow, but particle physics being what it is, there are many other theories for how matter came to dominate over antimatter that don't involve neutrinos. Maybe it was some X particle that makes up dark matter, though there's no evidence that it exists, or a Higgs triplet, though there's no evidence that this exists, or metastable WIMPs, or a technibaryon, or halogenesis, which requires 3 new particles, for none of which there's any evidence. And the kicker is that none of those theories even predicts the amount of matter or antimatter. This is because those theories all have equations that can be used forward in time and backward in time, and they uniquely connect one initial state to one final state. The amounts of matter and antimatter today are a consequence of whatever physicists assumed the universe started with. They have assumed the supposed problem into existence. What this experiment will do is measure some property of neutrinos. That it's something to do with our existence is a story they've made up, so it sounds more interesting. I'm not against this experiment. I mean, it's not my tax money after all. And in the end, it will at least prove that those $2 billion existed. If an alien spaceship lands on our planet and the doors open, what do you expect to see? 2 arms, 2 legs, 2 eyes? A bag of slime? A swarm? Could alien life have emerged in outer space rather than on a planet? And if we simulate bacteria in a computer, are they alive? The answer to all these questions hinges on understanding just what life is and how it comes about. Evolution seems a complicated and pretty random process, but in a recent paper, a group of scientists surprisingly says that if we could go back 4 billion years and start life on Earth all over again, the result might not be all that different to what it's today. Indeed, life all over the universe must follow similar rules. In their own words, computational, physical, and dynamical constraints profoundly limit the design space of possible living systems. One of the consequences, they say, is that we'll never get rid of parasites like viruses, because parasites are an inevitable consequence of social media. Evolution. They arrive at this rather startling conclusion by looking at what property a system needs to increase complexity. This circumvents the problem of having to start with a definition for life. The most obvious example is that if you want any sort of evolution and natural selection, you need a system that can store information and reproduce it with small modifications. Life on Earth currently does this in the form of DNA, and while that is a very specific molecule, the researchers say that long chains of molecules are the easiest and therefore most likely way for a system to store information. The second ingredient that life needs, they say, is what was already pointed out by Erwin Schrödinger. Yes, the one with the cat, about 100 years ago. It's that a living system must avoid entropy increase. If entropy increases, that'll eventually merge the system with its environment in a state of maximal disorder. As they write in the paper, each entropy-reducing reaction must be locally coupled to a free energy source, and continuing to do that requires reaction cycles. That's a sort of metabolic system. Next, they say that the metabolic system can work more efficiently if the system shields itself from the environment. That is, it'll develop a physical system boundary. Now take these three together and you have the basic properties of a cell. But that isn't it, because there's an easy way for these basic cells to reach higher complexity. It's to combine several cells and differentiate their tasks. The authors say that multicellular organisms are the most likely path to higher complexity because these groups of cells are particularly stable and their individual cells have proved to be robust already. They say that this gradual build-up works all the way to cognitive function, because as the system grows, it can find ways to gather energy and reproduce that are not possible for simpler organisms. That, however, doesn't make the simpler organisms go away, and indeed some of them will try to benefit from the larger ones. This is why they say complex life always has parasites. It's an inevitable byproduct of evolution. In summary, they say that it's highly likely that all life in the universe is made of differentiated cells, has metabolic cycles, stores information in long chains of molecules, and sits on the couch while watching YouTube. Just checking if you're listening. Basically, they say that a bag of slime isn't differentiated enough and a swarm isn't stable enough under environmental perturbations to reach higher complexity. But it's also interesting what this does not imply. It doesn't imply, for example, that life must have started on a planet. Indeed, some have argued that life could exist in gas clouds in interstellar space in the form of simple bacteria. This could work because it's so cold in these clouds that hydrogen is liquid. This means the hydrogen could be contained by cell membranes and the microbes could use it to transport molecules such as carbon monoxide from the gas clouds through the membranes. Another thing that the new study doesn't imply is the particular shape of the cell masses. So maybe alien life is made of cells like us, but it's got 7 legs instead, or breathes fire, or buys Twitter. That said, I'm highly skeptical that the argument that life must be of this form is correct. This is because it assumes that life emerged by natural evolution. But if you have sufficiently complex life, like humans, these can do their own artificial evolution. For example, AI researchers are currently trying to create a virtual cell. This has practical uses for testing drugs, but also raises the question of whether the virtual cell is alive. And if yes, what is to stop us from creating living beings in artificial physical environments that don't exist in the real world? Then again, maybe this isn't the real world either. Hello? Elon, I told you not to call me at work. Well, you could just have told them you want to go back to your home planet rather than taking over this one. I don't listen to what they say on X. It's all nonsense. Elon? Thanks for watching. See you tomorrow.